Okay, now I want to take this to the level that we're getting at this point in the interpretation process. And this has taken a long time to get to this point. A lot of the reason that it took so long is because of the lack of computing power, if you will. We're not reinventing the wheel here. We're reinventing the interpretation presentation, if you will, here. Because now we're just going to take all the curves, put them back on the paper, and we're going to start to reassign different scales to them. Because now we're working with this movable oil philosophy. Okay, I'm trying to establish how can I get to that interpretation picture without getting very complicated on all of these other things that we can get lost in the calculations. Remember, I talked about trying to work with side bed resistivities and all this. You can do that, but you're going to need a lot of time. So how can I do this? How can I put it on paper so that this speeds the process up? Well, if you look at something like this, I'll just call it, and just to give it a name, a comparative analysis header. This is what the curves would look like. And basically everything from here to the left is just the original logs. Okay? That would be a composite type presentation of all the logs that you ran. Everything to the right is going to represent that movable oil portion or interpretation that we would like to get to. And all that means is I just have to rescale things so that the lows and the highs correspond to the same endpoints, okay, relative to each other. So now instead of the resistivity, over here I've got it from 0.2 to 200. I'm going to rescale it based on this log from 0.04 to 400. And every log will be a little different, but these are coming from those resistivities that you get from the header. Okay? So whatever you saw on the header determines what these values are going to be. They're not numbers I picked out of thin air. They came off the header. Okay? So it depends on what the resistivity of the connate water or the formation water. For instance, if it's a 0.04, which is typical, that's a good Kansas number, 0.04 RW. You can see what the endpoints for that curve will be, 0.04 to 400. It will always be that for a 0.04 formation water. And looking at the shallow curve, which is, we're calling LL3, I now have two other endpoints. Off on the left over here, it was still 0.2 to 200 in the original presentation. Now you rescale it. Same thing with the microlog. If you're looking at the normal microlog curve, just rescale it. Now we're going to put the porosities. Now you'll notice the scale is a little different. In fact, it's going the other direction, but from 1 to 100%. And if I have a density, 1 to 100%, all the porosity scales will be the same. Even if I have a sonic, they're always going to be the same, 1 to 100. And if you actually had a cross-plot porosity, it's still going to be the same. And then if you see the top curve, all this is a, if you will, a gamma ray cutoff type curve. I'm putting this in here so if I don't actually want to see the shale zones, I can mask those shale zones. Aren't too many shale zones that we're interested in, right? So if I can somehow keep from seeing them, that makes my view of the reservoir a lot simpler. But by putting all those there, I can establish what the residual and the movable component is just by looking at it. So once I'm now working with, what's that program that John talked about earlier, Data View? I'm now looking at Data View and I'm just building this format. I only have to do it once. Build a format, then I can start to see where my hydrocarbon zones are, where my movable and residual zones are. Haven't put a pencil on a piece of paper yet, right? All I've done is push the curves around a little bit. So if we look at a suite of logs, and this is just like any log that you might run, except I've put them together, made a composite. This would be a dual induction with a compensated neutron compensated density curve on the right. And if I look at the zone, for instance, from 4440 down to TD, what kind of rock do you think that might be, since a lot of you have seen these? It's probably a sand or a chert, right? Where the neutron is reading less than the density. Probably a sand or a chert. Got pretty good resistivities that you see. So just inferring, and if I look off to the left, if I look at the caliper, it's got good mud cake. But what's one of the more important things to look at? The first thing you look at trying to determine where pay zones is. What zones have mud cake, right? Well, you notice what I've done in the middle track here. I've rescaled the caliper so that I always see instantly what zone would have mud cake. Because probably if I have a pay zone, it probably has mud cake, okay? That's one of the knowns, and that's one of the facts of life. So I'm very, very interested in what that is. What zones are that happening to? But if I have a chert or a sand with a lot of resistivity, now where might my pay zone be inside that? Most people aren't good enough just to look at this and say, well, it's right here or it's right there. So let's simplify it. Let's add those curves off to the right that I talked about where I rescaled them. Let's put them out there. Well, now I've got these definable colors that are showing up. Haven't put a pencil on paper yet, but these curves are starting to show up with these colors. Probably, again, we're looking at porosity to the left, resistivity to the right, right? This is that basic format that we came up with that Jim knew about. If porosity is going to the left and resistivity is going to the right, that's good. But probably if all of the curves are in agreement, like you see at the bottom of the page, if everything is stacked on top of each other, that's probably a wet zone. Okay? Now as those curves start to pull apart, I'm probably in a transition zone. I'm probably oil and water as they start to pull apart. And when they're finally pulled apart as far as they're going to go, that's why this is such a good example. As far as they're going to go, it's probably all pay. Okay? So if I'm going to pick perfs, it's going to be across that interval right there, right? Now your biggest dilemma is, what part of that pay zone am I going to perforate? Well, that is so far down the definition or calculation cycle that we're getting to that this is pretty awesome. Because now I just have to worry about where inside of there am I interested in looking. Okay? Haven't decided yet what's the water saturation anywhere. Don't really know, right? I can stop and check. Now that I know where the pay zones are, I can stop and check and see what it is. Now if you're going to have to calculate reserves, you're going to have to know, right? But at this point, if I'm looking at the log, I just pulled it out of the hole, what am I going to do? Well, in 10 minutes, I've got a pretty good idea of what I'm going to do, right? So we're going to go up and down the wellbore looking for these things. This just happens to be a real good example of what's going on. Again, porosity to the left, resistivity to the right. That's the thing that we're working with. And by working with the movable oil plot conception, if you will, we can establish what those endpoints were based on resistivities that we read off of the header. Okay? Header information directly to interpretation. Because now I'm working with those rings of influence that we talked about on the Schlumberger picture.